Think about your daily routine for a moment. You wake up, and a heating element inside your coffee machine holds the water at exactly 93 degrees Celsius. You get in your car, hop on the highway, and turn on cruise control. The car holds its speed at exactly 65 miles per hour. You arrive at the office, pull out your phone to snap a photo, and a mechanical suspension system instantly shifts the camera lens to cancel out the shaking of your hand. Outside, a commercial airliner cruises overhead. Its autopilot makes macro adjustments to the elevators every fraction of a second to hold an altitude of exactly 35,000 feet. Down on the sidewalk, someone glides past on a self-balanced scooter, its motors constantly fighting gravity to hold at 0-degree tilt. And underpinning all of this is the power grid, spinning massive turbines to lock the alternating current at exactly 50 Hz. Thermodynamics, aeronautics, robotics, and electrical engineering. These seem like completely different engineering problems. But if you look under the hood of the code running these systems, you will find the exact same, surprisingly short mathematical equation. An algorithm so elegant, it is quietly running almost every automated physical process in our modern world. In fact, across all industries, it is estimated that this single equation powers up to 97% of all automatic control systems. And yet, outside of engineering circles, almost no one has ever heard of it. It is the undisputed workhorse of what experts call the hidden technology of the modern world. It is the PID controller. The reason why this one algorithm is everywhere is because it does not need any complex mathematical model of the physical details of cars, airplanes, and so on. Instead, we can strip away the physical world entirely and represent our machine as a single blue dot. It doesn't matter if this dot represents temperature, altitude, or the speed of a car. We will call its current value the state. Above it is a yellow dashed line. This is our target, which we call the set point. For instance, 65 miles per hour. Our entire goal is to write a mathematical rule that moves the dot to the line and keeps it there, entirely blind to the physics underneath. Before we look at how this control system actually works, it's worth asking a fundamental question. Why do we even need a control system at all? If we know our car's exact weight and engine power, the solution seems obvious. Calculate the precise throttle needed for 65 miles per hour and lock the gas pedal. This works on paper, but the real world is messy. What if you hit a headwind or some slopes? By blindly holding that exact throttle, your speed will inevitably miss the mark. Because a pre-planned strategy never actually checks the speedometer. It is entirely blind. If anything unexpected happens, it has absolutely no way to realize it made a mistake. To fix a blind machine, we have to give it eyes. We need to close the loop by adding a sensor. The sensor measures the car's speed. The control system adjusts the throttle, and the sensor immediately measures the result. This continuous circular flow of information is a feedback loop, the mechanism that allows a system to survive the uncertainties and errors of the real world. To achieve this, the control system constantly compares two numbers, the current state and the set point. The algorithm only cares about the gap between them. Visually, this gap is simply the distance between our blue dot and the yellow line. In other words, this is the tracking error. Every control algorithm ever written is just a mathematical strategy for taking the error and squashing it down to zero. Armed with our feedback loop, what is the absolute simplest rule we could write? You may think of a binary switch. If we are below 65 miles per hour, floor the gas to 100%. If we are above 65, completely cut it. This is called bang-bang control, and it is exactly how a cheap thermostat operates. But in a heavy moving vehicle, the result is violent. Even if the computer cuts the gas at exactly 65 miles per hour, the car's massive momentum carries it right past the target. Eventually, friction drops the speed below the line, and so the system instantly floors the pedal again, and the car shoots past the target once more. The machine chatters back and forth in a jagged, endless loop of overcorrection. To get a smooth ride, we need a rule that scales its effort based on the size of the error. If the car is going at 30 miles per hour, the engine should push hard, but if it is at 64 miles per hour, it should only provide a delicate nudge. This is proportional control. Mathematically, we take our error, E of t, and multiply it by a constant, Kp. This constant acts like a volume dial. High means aggressive, low means relaxed. This is a massive upgrade over the violent on-off switch. But if you actually implement this, something absurd happens. The car will not reach 65 miles per hour. It will settle at, say, 62 miles per hour. At 62 miles per hour, there is a clear error of 3 miles per hour. The controller is actively pressing the gas. So why doesn't the car speed up? The answer is physics. Aerodynamic drag and friction are constantly stealing energy. To maintain speed, the engine must supply a steady baseline of power. Watch the math. If the car magically hits 65 miles per hour, the error drops to 0. Our formula multiplies by 0, cutting the throttle completely. But the car still has to fight friction. Without engine power, the car immediately slows down and it drops back to 62 miles per hour. Now, with an error of 3, the math wakes up and applies a small amount of throttle. As it turns out, this tiny bit of gas perfectly balances the drag of the road. The car stabilizes beautifully, but at the wrong speed. Our math is trapped. It can never reach the target because if it did, the pushing force will vanish. This permanent gap is called steady-state error. During the Industrial Revolution, this exact paradox plagued steam engine designers for nearly a century. It took physicist James Clerk Maxwell to explain the phenomenon in 1868, a paper that officially started the entire field of control theory. To solve this issue, our algorithm needs something the proportional term lacks: a memory. If you were driving stuck at 62 miles per hour, you wouldn't just freeze. You would realize that you have been below your target for a while and press the gas a little harder. So we need a mathematical tool that measures not just the size of the error, but how long it has been sticking around. In calculus, we do this by taking the integral. The integral calculates the accumulated area of the error over time. If the error is even slightly positive, like our stubborn 3 miles per hour gap, that mathematical area gets bigger with every passing second. We multiply this accumulated area by a new constant, Ki. This is our integral term. Watch how beautifully this interacts with physics. The proportional term does the heavy lifting, bringing the car to 62 miles per hour before becoming too small. But the integral term is quietly accumulating. As its area grows, it slowly turns up the throttle and nudges the speed up to finally reach 65 miles per hour. Now, what happens when we hit our target? The error is exactly 0, so the proportional term shuts off and the integral area stops growing. But, and this is the brilliant part, the area we already accumulated doesn't disappear. It stays exactly at whatever size it reached. But remembering the past, the integral term completely wipes out our steady-state error. Our PI controller is great, but it has an issue. If we start from a dead stop, the proportional and the integral terms push so hard that the car blows right past the target before eventually settling down. This is called overshoot. This may be just unpleasant in a car, but could be fatal in a robotic surgical arm or a drone navigating a narrow hallway. To fix this, the algorithm needs to look into the future. When driving toward a red light, you don't wait until the crosswalk to lift your foot. You feel how fast you're approaching and ease off early. So we need to measure how fast the error is changing. In calculus, this rate of change is the derivative. We multiply it by our final constant, Kd, to get our derivative term. When the car rushes towards 65 miles per hour, the error shrinks rapidly. The derivative term sees this steep drop and adds a negative force. It acts exactly like a parachute. intentionally fighting the gas pedal to brake early. The faster the approach, the harder it pulls back. The result is a beautiful damped curve, gliding perfectly into the target without a single mile/hour of overshoot. Proportional P looks at the present. Integral I remembers the past. Derivative D predicts the future. Add them together and you get a single unified formula, the PID Controller. What makes this profoundly beautiful is its absolute universality. You can take this exact same mathematical structure, leave the formula entirely untouched, and apply it to almost any real system. It can balance a drone in a storm, hold the speed of a massive cargo ship across the ocean, or guide the flaps of a commercial airplane. To switch between these vastly different machines, an engineer simply tunes the three constants Kp, Ki, and Kd, perfectly balancing how much the machine cares about the present, the past, and the future. You may wonder why this same algorithm is everywhere. The reason is that it is as simple as it is effective. It just works. If you enjoyed this video, please hit the subscribe button and see you next time.